Hello, everyone. This is Tarik Rashid. I'm going to present an nesting algorithm. It's a step-by-step practical example on how this algorithm can be implemented and can be used for solving different problems. And nesting algorithm, or sometimes we can call it ANA for short. It is basically metaheuristic algorithm. Of course, generally we have two types of algorithm: heuristic and metaheuristic. Heuristic, we can have trajectory-based algorithms or single solution-based algorithm. The example of this type of algorithms are hill climbing, simulated annealing, tableau search, variable neighborhood search, etc. Whereas population-based algorithm, metaheuristic we're talking about, metaheuristic population-based algorithm. That means we have multi-solution algorithm. So examples of these are genetic algorithm, particle swarm optimization, and nesting algorithm, etc. These are some examples of metaheuristic algorithm in the past: genetic algorithm and colony, PSO, particle swarm optimization. And those in yellow at the bottom, these are recent algorithms, very powerful: DSO, fitness-dependent optimization, child drawing development optimization, and nesting algorithm, which will be explained momentarily. Learner performance-based algorithm, evolutionary clustering algorithm, star and fox algorithm. And nesting algorithm is a nature-inspired population-based algorithm, is used for optimization problems. And the idea is extracted from ant nesting process in the nature. So Leptothorax ant colonies prefer horizontal crevices and build nests within flat crevices in rocks that provide the roof and floor of their dwelling place in order to defend themselves against physical factors and biological enemies. They naturally wall themselves into their chosen creeps by encircling themselves with a border of debris, or grains, which are particles of earth or small fragments of stones. The circumference of the wall is proper to accommodate their population, which can be around single queen, some eggs, and some 500 worker ants. The Leptothorax worker ants building behavior, which is inspired this algorithm, can be summarized as follows. Worker ants are responsible for building new nests by collecting building materials, transporting them into the nest sites, and releasing them in an area around the queen ant. Worker ants, again, make a random walk within the nest until they encounter their nest mates with stationary building materials to deposit. Each worker ant makes an independent decision about which direction to take around the queen for depositing. Worker ants, they tend towards the area with the most drop building material to deposit. Each worker ant selects an area around the queen ant to start the bulldozing process. A decision then is made when all worker ants in the colony are bulldozing at potential area. This table shows you the nature, behavior of the ant, and also as opposed to the algorithm. So worker ant means search agent, deposition position means potential solution, deposition position specification means fitness function, worker ant's decision factor, deposition weight, fitness deposition position means the best solution, nest mate or stationary stone, it means previous deposition position. Now, the algorithm started with initial process, which we have a number of ants, each one of them is an agent, and iteratively it finds the deposition rate and adds it to the current deposition of the position to find a new solution. So a new solution can be found by formula 9. This is formula 9. So search agent, or the solution in the next iteration, equals current search agent, which is the solution, current solution, plus the rate of change. So every time this rate of change is added to the current search agent or current solution in order to get next search agent or next solution. However, this change or rate of change can be found through this equation generally. This is a general condition 10. So it means TW, which is deposition weight, that factor, multiplied by the best solution minus the current solution. Now, we've got few conditions to find the rate of change. The rate of change can be either found by 11 or 12. In terms of 11, can be used when you have the current ant, the current solution equals the local best. Now, if this condition is true, then use 11. Or if the current solution equals previous solution, then at that time we use equation 12, which is R, random number, multiplied by the best solution minus the current solution. Now, for deposition weight, TW, deposition weight can be found by R multiplied by T, current tendency rate, over previous tendency rate. And we need to find T and T previous, which is current tendency rate, previous tendency rate. Now, using Pythagorean theorem, we can find T and T previous, which can be calculated through these two equations, 14 to find current tendency rate, which is x best minus x current over, square, best solution minus current solution minus best fitness minus current fitness square. Likewise, same thing for the previous tendency rate. The previous tendency rate, the best solution minus previous solution and the best fitness minus previous fitness, square and find T. By these two equations, we find T and T previous. Now, this is the algorithm flowchart. I go briefly on it. Start, initialize parameters, generate and generate ands randomly, and calculate fitness. Then initialize previous. So initialize previous, it is in the first iteration, initialize previous equals initial worker ants. So the values of initial worker ants equal to previous ants. That's only for the first iteration. Then in the second iteration, the change will happen, and then you wouldn't use this would not be applied in the second iteration. Now, while we are looping for each ant, we find local best and generate random R for each ant. Now we make a comparison. If ant equals local best, we use equation 11. Or if it's not, then ant equals previous, then we use equation 12. In case these two conditions are not satisfied, then we automatically will come to the equations 14, 15, 13, and 10. We use those equations, and then for all three equations, for all three conditions, we use equation 9 to get the new solution. Now, if the new solution fitness for the new solution is less than the current fitness that it has, then it will be accepted. Otherwise, we'll repeat to find local best for each ant. Now, when the termination is met or stop criteria is met, we will stop the optimal solution is found, and we stop the algorithm. Now, and nesting algorithm in the original paper implemented in Java, it has 4 classes: main, single objective, and functions. Now, the major contribution for this algorithm, it has been used for single objective optimization problems. The idea basically is taken mathematically from Pythagorean theorem, which is integrated into AND nesting model for generating convenient weights that assists the algorithm in both exploration and exploitation. The algorithm outperforms PSO, GA, DA, WA, and SSA. These are the existing algorithms, and the algorithm used for 2 engineering real-world problems. The algorithm also tested against some traditional and advanced testing functions. The algorithm outperformed those existing algorithms. Now, at least in this presentation, I'm going to give you a step-by-step of implementing a nesting algorithm, assuming that we have fitness function xi square sigma for 2 dimension, d equals 2, that means 2 dimension, and we have 3 agents, 3 ants, the population size. Now, each dimension bounds between 100 and minus 100, or minus 100 and 100. Now, well, in the first iteration, we randomly select 3 ants, and we initialize its dimensions. So first, initializing the worker ants, 3 ants, x1, minus 2, minus 1, 1, x2, 3, 0, 1, and the fitness minus 1, minus 2 square, plus 3 square, 13, minus 1 square, plus 0 square, 1. And we found from fitness function that ant2 is the local best because it has the least fitness function. It's a minimization problem. So we said that at the beginning, the previous population is the current population. So this current population, it is also the previous because we don't have previous yet. Now, iteration 1 for ANT1, we have random number, we select 0.3, and 1 and 1, 1. It has position -2 and 3, as it's shown in the table, -2 and 3. And in the first iteration, we'll see that this position equals to its previous position. So we said that this table, it is the same as previous. So this, it's equal to its previous position. Now we are going to use the condition which says that use equation 12. And then for finding the ANT for the next iteration, we use equation 9. Here's equation 12, R multiplied by x best minus x 11. This is x best position, -1, 0. That's -1, 0 in the table, -1, 0. And x current, which is -2, 3. X current, which is -2, 3, first ANT, -2, 3. And then we find delta, the change, which is position 1, 0.3, dimension 1, dimension 2, -0.9. Using equation 9 to get new solution, this add the change that we have. That's equation 9. I go to show it to you just in a second. That's equation 9. So the current plus the change. We found the change by equation 12. And now we're adding it to the current. So, and we will find, that's the new solution, -1.7. If you square it plus 2.1 square it, you'll get fitness 7.3. This 7.3, it is better than previous one, which was 13. So 7.3, the new solution, the new fitness function for this solution is updated, and it is updated in a way that it's better than 13. It's more or less than 13. That's 13. So we found 7.3, which is, we can accept the solution. If it's less, we can accept it. So the solution is accepted. We take it for the next iteration. Now we go to the next ANT, which is -1, 0. Okay, so -1, 0, it is equal to the best local. -1, 0, we'll see the table. It is equal to, it is the best local. So this solution, current solution, it's equal to the best. So we are going to use equation 11 in this case to generate step size. And we add it to, when we get the change, we add it to equation 9 to get the new solution. Now we get the new solution -1.30. That's the new solution. Get the fitness function for this one, -1.3 square plus 0 square, according to the fitness function in the slide that has been shown. So 1.69. This one cannot be accepted because it's greater than what we had for ANT2. For ANT2, we had fitness function 1, and the new solution is 1. The fitness for the new solution is 1.69. So this is greater, so it cannot be accepted for the next iteration. So we keep the existing one. Now for ANT3, 1, this is equal to the previous solution according to the table. If you go back to the table, then formula 12 is used to find the step size and to generate the ANT for the next iteration. We use equation 9. So here, equation 12, and this is equation 9. This one, equation 9, this equation 12. And now we found the fitness 6.5. for and tree. Now we'll see and tree fitness 6.65 is less than 2, so it can be accepted. It was 2 earlier in the first iteration, and now we update in the first iteration. We found it is smaller than that one, so it can be accepted. So once accepted, now the table that we had is now updated. The first solution is taken. The second solution, it remained, and the third solution is updated. So the table has been changed. So table 2, if you compare to table 1, this is changed. This one remained as it is. This one changed. Now, this is the least, and this is the local best. We found the local best is and 3 now. It was and 1, it was and 2, and now it's and 3. So the same thing. In iteration 2, we do the same thing. And 1, now minus 1.7, 2.1, which is here. Okay, and with fitness 7.3, we try to get this is neither equal equal to the best nor equal to the previous. So it is not equal to the previous. So if you just compare this and number 1, it's not equal to the previous table. This table, not equal. That's 13, and here is 7, and wasn't equal to, it's not equal to the local best. So we are going to the third condition, which is using equation 14 to get tendency rate, and equation 15 to get previous tendency rate, and equation 13 to get the change, and equation 10 as well. So to get DW, the position weight, and we use 10 to get the change, and we use 9 to get the solution in the next iteration. So here I put equation 14 to find tendency, current tendency, and previous tendency, equation 15, and deposition weight for first dimension. Likewise for the second dimension, equation 14, equation 15 for the second tendency rate, and equation 13 for deposition weight for the second dimension for the solution. Now, and use equation 10 to get the change, and add this to the current one, to the current value, that minus 1.7 and 2.1, 2 dimensions that we have. So this add to this, and this add to this, and you will find new solution with 2 dimensions, 0.4 and 1.8. Get the fitness of this 1.1.4 square plus 1.8 square, you will get 3.7. This will be accepted because at least 3.73 is less than 7.3. So that would be accepted. Likewise, we go for and 2. Because and 2 it's equal to previous one in the table. It hasn't been changed, so we use equation 12. And let's see, that is table 2. And if you go to table 1, this minus 101. If you go to table 1, it hasn't been changed, minus 101. So we use equation 12 and 9 to get the new solution. And once you found the new solution, get the fitness for them 0.65. 0.65, it is less than 2 that it has. So this solution will be accepted. 0.65 less than 2. So it's accepted. So it's accepted. So in this case, the table has been changed. You can see the table has been changed. So here it has been changed, and this one has been changed, and this one has been. Now the minimum is This is the minimum local best. And the algorithm continues iteratively until we get the best solution or the minimum solution, and then the algorithm stops somewhere when the stop criteria is met. So the conclusion, ANA results are more accurate when increasing search agent number. For example, if you increase the number of agents, and ANA algorithm keeps quite well balanced between exploitation and exploration. And also ANA can be developed for in the future for multi-objective optimization problem. Now, thank you very much for listening to this simple example presentation. The detail of the algorithm is in this link with pseudocode and source to find the package of the software. And if you have any problems, do not hesitate to contact me in one of these email addresses. Thank you very much, and see you with the next tutorial.